Assalamu alaikum. Welcome back. We live in a data-driven society in which we are practically inundated with data. We are consuming and creating data at unprecedented rates. However, how do we make meaning out of this data? How do we use this data to improve our standard of living or improve our decision-making process in the face of uncertainty? This session addresses this question by introducing the concept of statistics, which is at the very core of the scientific process. In this session, I'm going to talk about initially statistics, its philosophical meaning, and its application areas. Thereafter, I'd be introducing two broad categories of statistics, the descriptive statistics and the inferential statistics. And we'd be seeing how inferential statistics is so important to the scientific process, because all scientific processes require the inductive method, the employment of the inductive method, in which we generalize from particular observations. And statistics is the prime tool used by scientists to actually help in this inductive process. So let us begin. What is statistics? And what is the role of statistics in science? We're going to address this question in this part. Science is based on the scientific method in which we iteratively use the deductive and inductive methods of reasoning. We use the deductive method initially to make necessary conclusions or predictions that follow from a particular hypothesis that explains how the natural world works. And thereafter, we make observations and match the observations against the predictions. And if there is a good match, this actually gives us confidence in the validity of our hypothesis. On the other hand, if the observations do not match our hypothesis or the predictions made by our hypothesis, it is a sign that we need a better model. So I'm going to show you how science needs the science of statistics to actually help in this generalization process. So we've already seen the scientific method in which we have both the inductive method and the deductive method, in which we loop between these two processes in order to improve our understanding of the world. But we must understand that all scientific knowledge is not completely certain in a mathematical sense and in a mathematically rigorous sense. So we will never be able to prove something like we prove in mathematics by using scientific methods. So in mathematics, when we say a relationship holds in general, that means that you will never be able to produce a counter example. So 2 plus 2 is always going to be 4, no matter where you actually do this operation. And this applies to all other mathematical theorems as well. So you have a certain axioms, and then you deductively create new knowledge from these axioms or these theorems to create new theorems. And this new knowledge is certain if we assume the truth of the premises. However, science works in a different way. In science, we do not claim to know the absolute truth. What we do in science is that we make particular observations and then generalize those observations into a hypothesis, which explains the part of nature that we're considering. And if this hypothesis is a good explanation of how the things are actually turning out, we have improved confidence in this hypothesis. But in science, we always have probabilistic confidence in a hypothesis. And our knowledge in a particular hypothesis is always suspect to being suspended if we find a counter example. So we've already seen the example of if we've always seen only white swans, is this a sufficient proof that only white swans exist and there are no black swans? However, if we think of this as a proof in a mathematically rigorous sense, the appearance of a single black swan would contradict this hypothesis. So science actually is always susceptible to, scientific theories are always susceptible to being changed in the face of evidence. So the gist of all this discussion is that science actually makes probabilistic inferences about how things work, and we are not at any time certain. And how do we quantify the level of certainty that we have in a particular hypothesis, and how do we ensure that we are not generalizing from observations in a hasty manner, in a sense which is not warranted? So if, for example, we just observe a single observation, and if we make a broad sweeping generalization, this will be bad science. So the kind of induction we use in science is not naive induction, it is rational induction, in the sense that we take all care to ensure that we are not generalizing in a wrong sense. We use the tool of statistics here to actually inform us what generalization can we validly be making from particular observations. Apart from the fact that scientific knowledge is probabilistic, we also now know that the world or the reality is actually statistical rather than deterministic. This actually is in conflict with the dominant theory in the 19th century. So let me talk about the deterministic model of reality and the statistical model of reality. In the early 1900s, the dominant scientific philosophy was that we live in a deterministic world, which is ruled by certain physical laws that are waiting to be discovered. And if we can discover these physical laws, we can know the future exactly. So this overconfidence, as we would say now, was actually following from the success of Newton's law, Kepler's law, Boyle's law, to explain many physical observations. And the dominant view then is characterized by the view of Laplace, who you would know as the creator of Laplace transform, who said that if we know certain physical laws, and if we know the past and the present in enough preciseness or with enough precision, we can exactly predict the future. And to explain the apparent discrepancies between what the laws predicted and what was actually observed, Laplace invented an error function in which he clumped together all the sources of error, and his hypothesis was that this difference between observations and the predictions of the mathematical laws is because of the lack of precision of our measuring equipment. If the precision of our measurement equipment actually improves, we would see that the observations and the mathematical predictions would exactly be the same. So this mode of thought is known as the theory of a clockwork universe, in which everything happens in a deterministic sense, in a predictable sense. However, at the end of the 20th century, this theory actually took a lot of beating by new discoveries. The discovery of the existence of atoms in which you have electrons, in which their motion is not exactly predictable, but they operate in a probabilistic sense, in which you cannot simultaneously measure in a precise fashion both the position of an electron and its momentum. Also, this was the microcosmos, the world of very small things when we talk of electrons. Also, at very large distances, the concept of time and distance actually becomes fuzzy. And we've seen that time is a very important metric in the scientific method in general, and in the network performance evaluation studies in particular. So if the concept of time is fuzzy, then we can imagine how this would affect our view of the scientific world. It would not be so deterministic then. So this model was then thereafter even corroborated by further discoveries. For example, the discovery of chaos theory, in which it is said that even minute differences in the precision of input variables actually turn out to create huge differences in the output if we think of the output in sufficiently far away or distant future. As an example, weather is notoriously hard to predict even in the current time, and in the time of advanced technology we cannot predict weather beyond a certain time. So for example, I cannot state now what the weather would be like 6 months from now. All that we can do is we can make tentative predictions for a very short time. This is because we don't live in a predictable world, and even the physical reality follows what is known statistical laws rather than deterministic laws. तो मैं दो चीजें फिर बात कर चुका हूं. The first thing was that the scientific method involves some uncertainty. Now I'm saying that even the physical reality has this uncertainty or unpredictability. We cannot be very deterministic about how things would turn out because we only have vague ideas about the causal effects in the universe. Even our theories are only approximate. Furthermore, whatever data that we have, it is only approximate because whatever measurement we are taking can only measure things at some level of precision. If we consider a continuous variable even between two consecutive integers, for example 0 and 1, you have infinite real numbers. So when do we say that we have a precise enough value? Whatever value we measure out of any physical instrument is going to have finite level of precision. The same applies to any computer. All computers have finite levels of precision. So our data is approximate, nature behaves in a statistical fashion, and science gives us probabilistic inference. So when I say science gives us probabilistic inferences, that does not mean science is careless. Science is not careless, but the conclusions that we can draw can only be said to be approximate because of all the effects and of all the reasons I've mentioned. Also, all measurements, and because our data is usually the result of measurements, it has some random error. यहाँ error जब हम इस्तेमाल कर रहे हैं, it's used in an emotionally neutral sense. Error का मतलब ये नहीं है कि it's necessarily a bad thing. In fact, all measurements have random errors, and these errors are because of the conditions. So I'll give you an example. Let us consider the example of someone's weight. This weight, even something as mundane as someone's weight, is never going to be an exact measurement because firstly, weight is a continuous variable. So and it is compared to what we have assigned to be a measure of 1 kilogram. Also, depending on the time we take this measurement, the weight is going to vary. So for example, right after waking up, your weight would be less than it would be after taking a hearty meal. So these are some concerns, and also you have concerns of precision of measuring devices. So if you measure your weight on one device, weighing machine, and you go on to measure yourself on another machine, the chances are they will not be exactly the same because of the reason of random variation. Also, our data is usually incomplete, which means that we do not have a complete picture of how the world works. Usually what we have is a sample. So to illustrate the concept of a sample, you may consider the example of polling, which the poll results are often reported in newspapers. So imagine that you want to ascertain how many people as a percentage would vote for a candidate in the forthcoming elections. So this task is actually very difficult if you want to take a census, and we know that taking census is very hard when you want to measure every person in the population or take the opinion of every person in the population. However, we can actually learn a lot about the whole population by only having a sample of the population in which we interview some people of the population and get their opinion. if this thing is done correctly according to sound statistical practices, we can actually learn a lot about the entire population with a sample size as small as maybe 2,000 people. So this actually relates to the concept of sampling, which we'll be covering in much detail in a later session. So statistics actually helps us reason about uncertainty. And this world, because of all the reasons I've mentioned, is uncertain. We cannot be deterministic about things that will happen in the future. So I'll give you a quote by Descartes, the inventor of Cartesian geometry, who said that it is a truth very certain that when it is not in our power to determine what is true, we ought to follow what is most probable. So in fact, this idea of statistics and probability predates the current era, and in fact, even in the writings of Aristotle, you have mentions of probability and similar ideas. So because our world is uncertain, we need to make statistical analysis of evidence to make any meaningful conclusions, or gain any meaningful information from the data. Lastly, statistics also helps us find pattern in data, because data in itself is very boring. It's very hard to find a pattern in its data, in its native form. As an illustrative example, have a look at this slide in which I show 5 figures in which it's not very clear what is the obvious pattern here. So if we think of these 5 figures as data items, it's hard to find a pattern here. But what we can do is, and I'm going to show you, this data actually has a pattern. If we only draw 2 horizontal lines, one at the top of these figures and one at the bottom of these figures, you'd be able to find out the pattern. And let me make it more obvious. You see life written there. So this thing was not clearly apparent when we were looking at the inert data. However, when we did this statistical manipulation, this was obviously not statistical manipulation, but a surrogate for it. I'm showing you this because this is how statistics work. Data में से आप pattern easily नहीं determine कर सकते, but by making certain operations on the data, the meaning just jumps out of data, and that's what we want. We want to gather meaning from data. So in this part, we've mentioned statistics as a vital cog in the working of science. And we've seen that all data, all measurements are only approximate. Even the way the world works is statistical in a sense that we have rough ideas that how things will work, but we can never be exactly sure how things will turn out in the future. I now want to talk about descriptive statistics. In descriptive statistics, we actually talk about the data that we're given, and we do not make inferences about what population created this data. To understand this, we need some more terminology. I'm going to explain in a bit what a population is and what a sample is. But even before that, when we're talking of descriptive statistics, this is now a question of data reduction. You're given possibly lots of data, and just by looking at the data, you cannot make any obvious conclusions from the data. The process of descriptive statistics is actually to reduce the data into forms that actually conveys information about the data that you have. But the important thing is that in descriptive statistics, you only seek to describe the data that you have. You do not seek to describe the process which created this data. So now we will discuss what does the terminology of a population and a sample mean. So a population is actually referred to the complete set of data that you're interested in. So if we are interested in measuring the opinion of people regarding their opinion of who would win a forthcoming election, the population might be the entire the entire population of humans in Pakistan. And it's difficult to ascertain their opinion by taking a census. So the next best thing that we can do is to take a sample from this population in which we're not considering all the people whose opinion we're interested in, but only a sample of these people. This is called a sample in which we are only considering a subset of population. And if this sample determination is done in a sound manner, we can actually learn a lot about the population just by observing the sample. The key idea here is that our sample should actually be representative of the entire population. If your population has different kinds of people, different categories of people, people in different income classes or belonging to different professions, you may think of them as different blocks of the population. The sample that you have must have a similar proportion of these blocks in the sample as is the case in the entire population. So the best way which has been proposed to do this is to take a random sample in which all the members of the population are equally likely to come in the sample. I'll give you some more terminology. So there is some confusion about what data is. Data generally, when we talk of data, it is usually in a plural sense, in which it is said to be a collection of datums, where a datum is just a data point. But sometimes we can actually use data to refer to a collection of datums. So in this sense, you can also use data as a singular. We'll also be saying that even statistic or statistics, there is a confusion if it's a singular or a plural. A statistic is a technical term which we'll be just covering in a while, and statistics usually refers to the science of statistics, or it may refer to the plural of the terminology which I'm going to introduce in a while. So I'll be introducing this term now, but before that I'm going to talk of a parameter. So before talking of a statistic, I'm going to talk of a parameter. Parameter is a measurement that is done on an entire population. So if, for example, we're interested in measuring the mean value of certain parameter that refers to the entire population, we would call this a parameter in a technical sense. इस्तिलाह के तौर पर हम parameter इस्तेमाल करेंगे when it refers to the population. When we are talking about some measurement which relates to a sample, we would call this a statistic. For example, if you have multiple measurements in a sample, any statistical operation on this would give you a statistic. So examples of parameter would be the population mean, which is often written as mu, the Greek letter mu, and the population standard deviation, which is written as sigma. And if you note carefully, both of these are Greek letters, and they are used such for a reason. All the parameters are actually given Greek letters. So you can just eyeball a variable and see if it's a Greek variable, you would know, or if it's a Greek letter, you would be able to know that this refers to the entire population of interest. अगर हम mu की बात करेंगे, so this reflects to the entire population. In the example we gave, this would refer to the population, the human population of entire Pakistan. Parameter की जब हम बात करते हैं. जब हम statistic की बात करते हैं, it only relates to the sample. And if we talk of the sample mean, जिसको आमतौर पे हम एक variable होता है Roman letter, उसके ऊपर एक bar लगा होता है. So this actually relates to the sample mean. And we also have the sample standard deviation, and this is usually called S. If you note again, you have a Roman letter. So a Roman letter relates to a sample and a Greek letter relates to a population. To illustrate the idea of descriptive statistics, I'm going to give you an example, but we are going to see this in much more detail in another session. चूँकि descriptive statistics का मकसद data को reduce करना into manageable forms, we're actually going to see this in more detail, that what are the available operations that we can do on data to reduce it. Example would be, given a data, we want to find out the central tendency of this data. So आमतौर पे we take an average of that. If we want to see the variation in the data, we have statistical parameters for that. So we'll be doing that in another session. Now we consider an example that given some data, कुछ आपको measurements दी गई हैं, and these measurements are the heights of a sample of a population. So we're talking of a sample now, because we said descriptive statistics only deals with what is given. It does not make an attempt to infer the conclusions to the general population. तो आपको जो data दिया गया है उसको हम study करते हैं, and this may actually be a very large data set. So for example, if you're taking a sample of 5,000 people and you have these numbers, how do we make meaning out of this data? What, for example, if we ask the question कि आम तौर पे एक typical human being की कितनी height है, we cannot make sense of this question, or we cannot answer this question by observing data in its entirety. We have to reduce the size of the data in a sense which is relevant to the question we are asking. So we may take data and calculate certain statistics from it. Note the word statistic. We are referring to a sample, so we use the word statistic here. The median height of the members of this sample is 5 feet 8 inches. We are actually showing this statistic both in a numerical format and also in a graphical format. We're using the box and whisker plot, और graphical format में हम 5 statistic को एक साथ दिखा रहे हैं. तो पहला statistic था median. The median ignores lots of information in the data. तो आपको सिर्फ median देख के नहीं पता चलेगा कि data में extreme values हैं कि नहीं, आमतौर पे कितनी variation है around this average. उसके लिए when we draw a box and whisker plot, we also give the highest value and also the lowest value. Sometimes the ranges, this is known as a range, the highest value and the lowest value. Even this may be not very representative of the actual data, क्योंकि ऐसा हो सकता है कि आपके पास एक outlier हो, and that is the highest, or you may still have data centered very closely around the mean. So we also have 2 more statistics in the box and whisker plot, and these are the percentiles. Percentile का मतलब है कि अगर हम data को arrange करें in a particular order, let's say in a decreasing order, तो हम देखेंगे कि if we divide the entire sample into 2 sizes, the middle value would be the median, in which half of the values are more than this and the other remaining half are less than this. So this would be the median. In a sense, this gives us the central tendency of the sample. इसके अलावा 75 percentile का मतलब ये है कि 75% of the data is actually less than this. 25 percentile का मतलब है कि 25% of the data is less than this. Median को हम 50 percentile भी कह सकते हैं, because median by definition is something which comes at the 50% mark. 50% of the data is less than this and the other is higher than this. So this wraps up our discussion for today's module about descriptive statistics, in which we said that in descriptive statistics, we actually only describe the sample or the data that we have, and we do not try to make inferences about the population which created this sample. तो अगर हम network performance evaluation की बात करें, and if we have simulation results, if we are talking of descriptive statistics और हमारे पास 10 readings हैं, तो हम सिर्फ जो 10 readings हैं उन्हीं को describe कर रहे हैं. We're not trying to understand the process which created this data. If we want to do this, we would be making use of inferential statistics, which we'll be covering next. Let us now talk about inferential statistics. Inferential statistics, in distinction to descriptive statistics, does not seek to only explain the data that you have, but it also has a more ambitious goal. It seeks to describe the population which actually created this sample. या ये जो sample हमारे पास है, जिसका data हम observe कर रहे हैं, ये किस population के अंदर से निकला है. So if we want to make inferences about the population, given a sample, we want to describe the parameters of the population, we have to make use of inferential statistics. And it should be clear to you that this is very vital for all sciences, because in science we have particular observations which we can think of as belonging to some hypothetical population which is actually creating this data. And we actually want to know something about that process and not just the data that we have. So we'd be seeing that inferential statistics is at the very heart of what statistics can do for a scientist. In descriptive statistics, we only focused on reducing the data into presentable forms in which we have almost a complete description of data. So we said that not all descriptive statistics capture the entire data, but with the combination of different statistics, you can actually know a lot of data in a more readily recognizable form. In inferential statistics, we use probability as the workhorse of inference because we are trying to extrapolate from the sample to the population. And this is no mean task because given just a very small sample, which is in any case just a subset of the population, we want to make conclusions about the population जिसके बारे में हमें पता भी नहीं है. But using inferential statistics, we can actually get to know a lot of things about the population. And furthermore, we can also quantify our uncertainty in this. So we would not only be able to say that, you know, the population parameter is presumably this, but we can also say, for example, that we are 95% confident that if we do this thing many times, 95% of the times the population mean, as an example, would be in a certain range close to what I am predicting. तो दो चीजें उसमें हो जाएंगी कि एक कितना confidence है. This confidence can be 95%, 99%, and it also gives a margin of error. So when we get to further topics in inferential statistics in future sessions, we'd be reading, we'd be understanding a lot more about this. But for now, we again stress that in inferential statistics, we use the tools of probability to make inferences or extrapolations from the sample to the population. That, okay, the sample is like this, but what will the population be like? So as an example, let me show you a clarifying example in which I'm going to show you the application of inferential statistics. If given a data of the heights of people in a certain sample, you only calculate the average height of people's height in this data set. This is what is known as descriptive statistics. But using this information, if I want to infer about the population's average height, this would be known as inferential statistics. And the process on which inferential statistic relies very heavily on is the usage of appropriate sampling. Sampling is very important, and the process of sampling is simply selecting a sample from a population. So let us have a look at this figure in which we are seeing some interesting things. The first thing that we are seeing is that we are having certain numerical values being output as measurements. So we have some values 89.7, 81.4, 84.8 and so on. And these measurements can actually be thought of as coming from theoretical population, या इसको हम कह सकते हैं hypothetical population एक है. इसकी वजह इस तरह सोचने की ये है कि जब भी आप measurement करते हैं, you're not going to get the same value. Exactly वो value आपको नहीं मिलेगी. Most of the times you'd be having some random errors, and these random errors are not blunders. Blunders होते हैं जब आप कोई value लिख रहे हैं, आप decimal आगे पीछे कर दें. That's a human blunder. We're not talking about that. We're talking of errors जो कि unavoidable हैं. Every time you make a measurement, you're going to have a slightly different value due to chance only. या आपका हो सकता है ambient temperature जो है वो आपको affect कर रहा है. Yeah, maybe it's just the time of the day. But whatever the cause, even if you're trying to keep the conditions as similar as possible, you're always going to have random errors. तो इसलिए हम सोच सकते हैं कि whatever measurements that we have is only a sample. And given this sample of maybe 10 readings or 20 readings or 50 readings, we want to make inferences about the actual process. And that actual process may be described by a probability distribution. in which, as shown in the figure, typically the mean value is shown to be around 85 and you have a spread of values around it. इसका मतलब ये है कि आम तौर पे आपकी measurements 85 के आसपास होंगी, लेकिन it will never be 85 in all cases because you have a probability distribution. Distribution का मतलब है कि you would have values which are centered around this but would have random variation. So in this case, you even have some extreme values of close to 93 and some very small values close to 75. But most of the measurements would be around 85. The important thing is, जो हम sample ले रहे हैं from this probability distribution should not be very small. If your sample is very small and you happen to get an unrepresentative number or collection of unrepresentative numbers, then you would be making inferences which are actually not accurate. They may be misleading. So sampling में आम तौर पे we focus on having an appropriately large sample and also we take pains to ensure कि हमारा sample जो है उसकी probability distribution या उसमें जो values हैं जिस तरह distributed हैं, it should be as close as possible to the actual population or the process which is creating this data. तो उसके लिए the best bet that we have is to actually do random sampling. And we will study this concept in much detail when we study sampling later on in this course. Another area in which inferential statistics are used is hypothesis testing. In hypothesis testing, we want to see the soundness of a hypothesis. And we base this assertion of the soundness of a hypothesis on statistical grounds. We don't want to conclude something on the basis of chance alone. Whenever we want to accept a hypothesis, we have to ensure that it is due to a cause and not simply on the basis of chance. Shall we be accepting any hypothesis? So to illustrate the ideas in hypothesis testing, let's have a look at an example. So as you can see in this slide, you have two methods, and the standard method is the one which we're currently using. This is the status quo. And we are modifying this method, hopefully in an attempt to improve the performance. So we want to then ensure if this modification actually improves the result or not. So as we can see, the standard method can be depicted as a probability distribution in which the observations are centered around a mean. And this probability distribution is a normal probability distribution which has the familiar bell-shaped curve. So most of the observations of the standard method would actually be very close to mu A, and you would have some variations on either side of mu A. The modified method, on the other hand, is shown also as a probability distribution. We must note here that when we are doing the experiments, we don't know the probability distribution. ये एक तरह से यहाँ दिखा रहा है कि असल में इनमें ये फ़र्क है. Actually, modified method in this example is better than standard method, and we want the mean value to be higher. So we see that mu B actually is higher than mu A. So you must remember and recall that we've mentioned that we use Greek letters for parameters of the population. So इस case में असल में the mean performance of the modified method is better. But we are only going to see the samples, and based on the sample we have to conclude if the modified method is better or not. इस case में, because we are setting out the example ourselves, we know that the mean value of modified method is better, but we don't know when we're doing an experiment. So on the basis of the observations, even if the observations show that the modified method is better, it may still be only due to chance, because due to chance हो सकता है कि असल में modified method ज़्यादा बेहतर ना हो, or even there may be no difference, but just due to chance alone, चूँकि आपने एक particular sample लिया है which is often of not a very large value, तो उस case में आपकी measurements हो सकता है by chance ज़्यादा आ जाएं. So we want to rule out this element of chance and only conclude that modified method is better if it is really better. So this really better will be made precise very soon. So we then are in a position to define two hypotheses. Null hypothesis is the status quo. Null hypothesis usually हम इस्तेमाल करते हैं to denote no effect. जो भी हम effect proof करना चाह रहे हैं, again this proof will be made more precise. Whatever hypothesis we want to actually show, null hypothesis is that this effect does not exist. The alternate hypothesis is that this effect exists. So in this case, the null hypothesis would be that there is no difference between the two methods. The alternate hypothesis, which we're interested in, showing to be acceptable, is that the modified method is better. So the most important question in hypothesis testing is that in what conditions can we reject the null hypothesis and instead adopt the alternate hypothesis. So we use the word reject here, and this distinction, this subtleness is important, because rejecting something is not the same as proving something to be false. चूँकि हम scientific observations की बात कर रहे हैं, on the basis of scientific observations and inferences made on the basis of that, our conclusions are always going to be probabilistic. So we can never be 100% certain that a hypothesis is true or a hypothesis is false. This is true in most scientific inquiries and studies. So what we can do is that we can, if the probability is very high, we can then adopt that hypothesis. If the probability of a certain hypothesis being true in the face of evidence is very low, we can reject the hypothesis. So इस case में हम null hypothesis को तब reject करेंगे जब the evidence is so extreme that if the null hypothesis was true, we would almost never have these observations. So this almost never is a subjective thing which is made precise by a value which is known as alpha, also known as significance level. कि कितना error हम बर्दाश्त कर सकते हैं, यानी how much error do we want to withstand that the null hypothesis is true but we are rejecting it. Because even if you have extreme results which are inconsistent with null hypothesis, it may still be true, because rare things by definition happen rarely. So this may be one of those rare occasions, but in the field of statistical hypothesis testing, we then settle on a level. आमतौर पे this level is 5%. यानी हम इसका मतलब ये है कि if the null hypothesis is true, we will only reject the hypothesis when the probability of having the results as extreme as those observed is less than 5%. In that case, because that null hypothesis becomes untenable, या हम इसको कह सकते हैं कि it becomes unacceptable. So it would be fair to reject the null hypothesis, और उस केस में हम कहेंगे कि we adopt the alternate hypothesis. Again, we don't say that we are accepting the alternate hypothesis, because that has the implication that the alternate hypothesis is true and the null hypothesis is false. We don't make that conclusion as statisticians. We don't say that we are either proving the null hypothesis or disproving the null hypothesis. हम किसी भी hypothesis को ना prove कर रहे हैं ना disprove कर रहे हैं. We're only rejecting it, rejecting the null hypothesis if the results are very extreme in the light of evidence, or we fail to reject the null hypothesis. So this distinction is important. लेकिन हम informally भी बात करेंगे having this thing in our mind. We already know that we're not proving and disproving the null hypothesis as such. तो उस case में हम बात कर सकते हैं of accepting the alternate hypothesis. Another area in which inferential statistics are used is regression analysis. And regression analysis is fitting a mathematical or a statistical relationship between the variables of interest. So often this is done between two variables, and if we're talking of linear regression, we try to think of a simple linear function which is relating these two variables of interest. So as you can see in the slide here, we have some observations, and you can see that all of these observations do not align themselves on a singular line. So we can easily visualize the relationship as non-linear. Lekin for simplicity, we may say that, okay, we are adopting a linear regression model for it, and you would have certain errors. So we choose a line which gives the best fit for all the observed variables, and then we say that these two variables are related in this manner. We can also use a non-linear regression model in which we are approximating the relationship between the two variables by a non-linear function. And we would be covering this when we talk of regression later on in this course. Now I would like to wrap up this session by concluding. I'll be making two remarks about statistics. The first one is that statistics is essential for all scientific disciplines because it helps you to quantify the level of uncertainty in your measurements. And all the sciences, because they are based on measurements and on empirical observation, they absolutely need this science to give an estimate of how much confident you are in your conclusions or how much uncertainty exists in your measurements. The second thing is we would use statistics often inferring something about the population given just a sample. क्योंकि आमतौर पे when we are doing experiments, we only have a sample of results. If you were to do this experiment again, the results would be different. Even if you're taking multiple measurements, if you do this experiment again, the results would be different. So statistics, and more specifically inferential statistics, helps us to estimate parameters of the population given just a sample. Also, descriptive statistics are important when we want to describe data and understand the patterns of the data and summarize it so that effective decisions can be taken. So with this, I conclude this lecture, and I'd be seeing you next time, inshallah. Assalamu alaikum.